Welcome to our fourth and final video series, I guess, for Unit 1, covering vectors and matrices, where in our final section, we're going to be looking at matrix multiplication, specifically multiplying two matrices A and B, and then in some later videos, it looks like it's probably going to be part 2 and mostly part 3 videos, multiplying two specific matrices CR, where we'll get a little bit more detailed into what those are, but they are going to play a big role once we get into Unit 2 in helping to solve a couple of different problems. A lot of these ideas, if you've come into this class having seen matrices and how we multiply with matrices before, should seem at least a little familiar on the upfront, specifically in this video. I think there's still some important takeaways though, so if you're following through and watching these chronologically, that you still continue to watch this video and kind of hear out some of the pieces that you may not necessarily think about, especially if you're coming in with that prior knowledge for multiplication, because I think there are, again, some big takeaways here and maybe some things that are phrased a little differently than what you've seen in the past. I'm also going to use a Purple Expo, these glass boards, which I know you can probably tell, even though I've bounced around a couple learning studios here at Mount Vernon, they're very reflective because of our windows, and I felt like this marker died really fast, so I want to use this purple one instead. When we're talking about matrix to matrix multiplication, there was one thing from the first set of videos that I had mentioned, that we have to ensure that if I'm multiplying two matrices together, let's say two matrices A and B, if A is an n by n matrix, then B needs to be an n by P or an n by M, or really can be any number of columns, but the number of rows needs to match the number of columns in matrix A for this multiplication to work. So say, for example, matrix A is a 3 by 2 matrix, then matrix B would have to at least have 2 rows, and then the number of columns could be anything like 4, for example. So A times B, this multiplication would work. The resulting matrix would be of the form 3 by 4, so it's these remaining outside dimensions that would essentially correspond to our resultant matrix. But another reason why I wanted to choose these numbers is that if I reverse this order, so instead of AB, if I wanted to multiply B times A, then these dimensions don't align, and I cannot actually perform that multiplication. And this is a property that we'll talk about towards the end. Just like with numbers, how we have commutative laws and associative laws, we need to look at that in terms of matrices and multiplication to see if those follow suit as well. You can kind of see in this case, AB doesn't necessarily equal to BA, so that associative law, if I remember right in terms of terminology, because selfishly I always mix those two up. The commutative law is not always true, which is what that one is. But we'll find out the associative law is, and is okay. So we have to make sure that these inner dimensions, the number of columns in our first matrix matches the number of rows. And a lot of that comes from this, the concept that this is a lot of dot products. Even when we're looking in terms of vector multiplication in columns, that everything has to line up. And so what we're going to essentially set up is that let's let B be equal to B1, B2, B3, all the way out to BP. And so this is essentially creating column vectors for B, and P is some number. Well, if A has the dimensions essentially match, like we talked about, let's just keep the same definition from earlier. Then if I want to do A times B, this is the same thing as doing A times B1, and then A times B2, then A times B3, all the way out to A, B, P. And when I'm multiplying matrices together, I'm essentially multiplying the first matrix with the column vector of each column vector in the second matrix. And I apologize for the wording or the deep breaths. And just to help illustrate this, let's let A and B both be a 2 by 2 matrix. So start with some of the more simplest cases. Specifically speaking, giving you kind of an introduction into what an exchange matrix looks like. And this plays a big role in how we manipulate manipulate matrices. Let's call this exchange matrix B is 0, 1, 1, 0. You'll notice it's very, very similar to an identity matrix for a 2x2, but you'll see that either you can think about it as the columns being swapped or the rows being swapped, which is really important because what it will end up doing, depending on how we multiply, swapping the rows or swapping the columns. If I let A be the matrix 1, 2, 3, 4, if we follow that sequence, then if I multiply A times B together, like previously defined, I can view this as AB1, I don't know why I wrote it as an index, and then AB2. So if I have AB1, this is the matrix 1, 2, 3, 4 times 0, 1. I have AB2 is 1, 2, 3, 4 times 1, 0. Matrix to matrix multiplication is really just a matrix and vector combination and multiplication, and a combination between those. And so it's kind of fascinating, especially as you start to get in and kind of practically do this. I even don't remember thinking about it in terms of columns and looking at it in this way. And so I think this is a really nice way to visualize the multiplication and what's happening, is looking at it in terms of this column approach. Versus when we're actually doing the calculations, we kind of more think about row dot products and kind of going row by column, etc. And so we know that when I'm doing this multiplication, we can think about it in terms of I'll look at it in terms of a row picture as 1 times 0 and 2 times 1 and doing that combination. And so if I do that dot product, 1, 2 with 0, 1, we get 4. If I do that same multiplication here with 3, 4, I get, I did that wrong, sorry. This entry is 2. This entry would be 4. So the first column here would be 2, 4. If I do that same multiplication here, thinking about it like dot products, I would have 1, 2 dotted with 1, 0, so that gives me 1. And then if I have 3, 4 dotted with 1, 0, I get 3. So this gives me my final matrix of 2, 4, and 1, 3 as my final. And I want to do a quick check, and I want to pop up the screen. Just want to make sure you can still see that. So this would be my final multiplication. If I compare that with the original matrix, notice that the two columns have been swapped. The rows have not been affected. So this is an exchange matrix, and specifically if I multiply AB, it's exchanging the columns, which is a really important kind of observation to make from that piece. Now, to help kind of see column view versus row view, what if instead of doing like an exchange matrix, what if we chose other numbers so you can kind of get a feel for how those calculations work? And so let's keep A as the same matrix, but I just want to kind of give me a little bit more space so I'm not crouching over too much. Getting older and can't bend over as much. I've also found that teaching for so long, the lower I write, the more crooked I go. So to kind of maintain some kind of nice, neat lines. Let's say matrix 1 again is 1, 2, 3, 4. Let's say matrix B is 5, 6, 7, 8. So, real fancy, just kind of counting in terms of whole numbers. If I want to do A times B, again, the way that I'm kind of thinking about this is I'm looking at this as A times 5, 7. And I'm looking at this as A times 6, 8. And I'm trying to construct this overall matrix. And finding and performing this multiplication, we have two specific ways to think about it. So let's say we want to look at it in terms of this first one. So let's do just this one to begin with. I have two approaches. So the first approach, which is kind of what most people tend to think, it's how I teach this in Unit 0 and get you to think about it. It's how most videos would essentially outline it. And I know I've said this a lot, but I just feel like I cannot emphasize it enough. The idea is dot products with the rows. So in other words, by taking this row and performing a dot product, this first entry would be found by doing 1 times 5 plus 2 times 7. The second entry would be this row dotted with the columns, so 3 times 5 and 4 times 7. So overall, there are 4 different multiplications that would construct the first column and the multiplication of A and B. Again, 1, 2, 3, 4, just to kind of see that. So that gives me a resultant of 4 and 14, 5 and 14, so 19. And then 15 and 28, which gives us, because I'm going to cheat, 43. So we have 4 different multiplications to find my first column vector in AB, and I get 19 and 43 for this. Again, this is kind of the row dot product idea of matrix vector multiplication. To find the second one, I would do A times 6, 8. And again, if I think about this in terms of the row picture, 1, 2, 3, 4, I'm going to dot these 2 rows with 6, 8. And so again, I have another 4 multiplications, 1 times 6 plus 2 times 8, and then 3 times 6 plus 4 times 8. This gives me a final vector, and again, of cheating, 2250, movie magic. In total, there are 8 multiplications that are being performed when I look at the row dot product multiplication technique. And again, most people tend to, when given numbers and performing matrix multiplications, approach it in this manner. They're actually doing row by column dot products and calculations. Also, one thing to just kind of point out, because I had this wrong assumption when looking at the multiplications that Dr. Strong talks about in his textbook. I was thinking about it in terms of operations, having taken some computing classes and numerical analysis classes. The number of operations performed impact the memory and speed and efficiency of a program. And so if you were trying to program matrix vector multiplication, I wanted to think about, when he talks about 8 multiplications, as 8 operations, which didn't feel right, because if you're counting plus signs, etc., like that's not the total number of operations. But he's not talking about operations. And so just to really kind of emphasize, when he is counting this 8, and when we look at something in a minute in terms of a generalization, he's looking at the number of multiplications, just to really kind of specify that. But this is one way that I can look at A times B. I can view these individual matrix vector multiplications as row dot products. There we go. Well, we can also look at it in terms of column combinations. So we can look at it in terms of linear combinations. And so just to kind of illustrate one aspect of that, let's look at it. Now the book flows kind of shows what this looks like for AB2, so I thought I could show it for AB1. Another way to help illustrate this idea is to take 5 and multiply it by the first column of A, and then add to it 7 times the second column, because when I'm doing this, this is another visualization for this matrix and vector multiplication. This matrix is applying to this vector this specific linear combination. And so notice again, and count the number of multiplications for the column view. 5 times 1, 5 times 3, 7 times 2, 7 times 4, and then we add those things together, we're going to get 19 and 43. And again, the number of multiplications is still 4. I get 2 here and 2 here. Now, if I do this for both columns, then that gives me a total of 8 multiplications. So even when you're looking at this and you compare this with the dot product that we did, the actual operations in the numbers is exactly the same. So whether you want to look at it in terms of a column viewpoint and looking at it as linear combinations, or looking at it as row dot product, physically speaking and doing this work, they're the same thing. There are 2 strategies to get to the same result. So from our standpoint, it's really how our brains work, which tends to be more of this style, the row and dot product. But if you're working in terms of computer programming and trying to create an efficient software, it may not be the case. Typically, and he gets into this a little bit, and it's been years since I've done a numerical analysis course, so I can't speak to it too much. But when a computer is storing information and trying to recall that information for operations, they tend to do better if that information is larger. And so performing in terms of these column operations can sometimes be a little bit faster than it would be to perform a bunch of row and dot products in smaller pieces. And so breaking it down this way is important for later applications of linear algebra in terms of computer programming and software. So this kind of illustrates how we can multiply two matrices and how really two matrices being multiplied together is really just matrix and vector multiplication. Right? It all stems from that. And hopefully this also kind of helps illustrate how the row way and column way multiplications will always come out to be the same. And he gets into some generalizations in terms of rows and columns and kind of talks about, since we're dealing with the 2 by 2, how that's going to be 8, 2 times 2 times 2 overall. As the matrices become more rectangular, the setup that he gives is a little bit more helpful. Now, already kind of showed a little bit that if we start to think about what rules or what laws can apply to matrix multiplication, the question becomes, well, is matrix multiplication associative? Is matrix multiplication commutative? If I multiply it by 1 or the identity matrix, will it always result in the original matrix? What can I do in terms of this? And so just as a couple of examples, when you deal with multiplying with general numbers in a real number system, for example, if I have 2 times 3, this will give me the same result as 3 times 2. The order of the multiplication does not matter. The answer will always be the same. And I've already kind of illustrated a little bit. This is not true for matrix multiplication. If I let A again be the matrix 1, 2, 3, 4, and I let B be the matrix 0, 1, 1, 0, remember this was that exchange matrix, we found that if I did A times B, the columns got swapped. This became 2, 4, and 1, 3. So multiplying A by the exchange matrix swapped or exchanged the columns, column 1 and column 2. Well, if I reverse the order, because in this case I can, notice that matrix A is 2 by 2, matrix B is 2 by 2, so even swapping these, those inner dimensions would match. Now I'm not going to get the same matrix. It just happens that it won't be that way. And to show that, let's do matrix B times these individual columns. And so I'm just going to quickly do it in terms of the dot product. So this dotted with this column ultimately will give me 3 and then 4. 1, 0 dotted across the board will give me 1 and then 2. Notice BA does a row exchange. It swaps row 1 and row 2. So depending on the order of the multiplication with this exchange matrix, we'll either swap the columns or swap the rows. And because the matrix is defined the way it is, those two resultant matrices are not the same. So this is not equal. And so the commutative law doesn't always hold. Sometimes it can. And there's some important properties and things that we can get into and we'll get into when that happens. But generally speaking, it won't work every time. So the commutative property is not a law when it comes to matrix multiplication. Now the associative does work. So commutative again is about swapping the order of the multiplication. The associative is all about what if I have 3 things being multiplied? Does it matter the order that we multiply? Because one thing I like to always tell my students, whether you're performing any of the 4 basic algebraic operations, addition, subtraction, division, multiplication, each of these are binary operations, meaning that you can only add 2 things at a time. You can only multiply 2 things at a time. So when I'm given 3 things being multiplied together, for example, 2 times 3 times 4, I can either do 2 times 3 first, and then times 4, or I can group 3 and 4 and then multiply by 2. And notice that we get the same answer. With numbers, multiplication is associative. We can associate in any order that we want to. We'll always get the same answer, but we have to pair up. We can't do 2 times 3 times 4 all at once. It's either 2 times 3 and then that result times 4, or vice versa. Well, for matrices, that also actually applies. And to help show that, let's use the same matrices for A and B. And what we're going to look at is, well, what if I have B times A times B? So here are my 3 matrices, and it looks kind of weird because we're using B twice. But the idea is that if I do B times A and then multiply that by B, is that going to give me the same thing as if I did A times B first and then did B? Now what's kind of nice is we've already done a lot of this legwork, and we've already kind of talked about what happens when I multiply by B on either side. So remember that B times A exchanged the rows of the matrix A. So B times A is 3, 4, 1, 2. Well, if I multiply this by B again, because B is on the right-hand side, this changed the columns. So if I change the columns, this gives me 4, 2, and then 3, 1. If I do A times B first, so just to put B out front, again, this is going to swap the columns. So this gives me a second matrix of 2, 4, 1, 3. And now by multiplying B in front, that is going to swap the rows, which we've seen before. And notice how that gives me 4, 3, 2, 1. We get the same result. And this is true even if I was to generalize it. A1, A11, A12, A21, A22, same thing with the B's. And we write out all of that multiplication, we would end up getting the same result as a way to prove this. But it shows that matrix multiplication is actually associative. That law holds. It also kind of shows you that it doesn't matter, and this is kind of the other reason why I'm using A, it doesn't matter if you want to swap the rows and then swap the columns, or if you want to swap the columns and then swap the rows. Because remember, B is doing an exchange, and if it's out front, it's rows. If it's behind, it's columns. Because the associative law is true, it doesn't matter the order that we do that. We can either swap rows or swap columns when we're dealing with the matrix. However we choose to perform that order has no impact in terms of the final. We can do it in either way we want to. So if you wanted to swap row 1 and row 2 and then swap 2 columns, that's the same thing as swapping 2 columns and then swapping those 2 rows. That result will always hold true. The last one when it comes to matrices is that distributive law, words. And just to write it out, but not really dig too much into the proof of it, we have that A times the sum of 2 matrices is equal to AB plus AC. If we can distribute the multiplication for A, the big thing we got to remember is that I cannot swap the order. So if A is being multiplied on the left-hand side, then A needs to be multiplied on the left-hand side of each matrix to maintain that equality. Because remember that the commutative law is not true, or at least is not always true. It's not a law, so we cannot apply it. So we have to be really, really careful in the order that we write things, because especially when using numbers and algebra, polynomials and things like that, you might be used to being able to work in any order, or if I was to do a parentheses of B plus C, then times A, this is a very different result because I'm swapping the order of that multiplication. So we just have to be very, very careful. And so that kind of really fleshes out the first video that I'd like to do for 1-4, talking about the multiplication, the ways that we can view that multiplication, as well as the associative law, distributive law, and commutative law, the main laws that you see when it comes to numbers. Where we'll go into now in the next couple of videos is we'll start looking at this rank 1 matrices. We had the building blocks in that last unit, in the last video. And then getting into what I like to call matrix factorization. So breaking a matrix down into 2 other ones. And that's what I was referring to at the very beginning of this video with C and R. C is a very specific matrix, so not random letters. To notate that. Same thing with R. And so we'll see what those are as we kind of round out And so the idea is to break this into two more sections just to help simplify this lesson down, because there's a couple different calculations and things to look at. Otherwise, I'll break this down into a little bit more. Otherwise, that's it for the first one.